Hello, welcome to the course SJPHY3BO3 Electrodynamics 1. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. We'll continue to discuss topics from Chapter 5, Magnetostatics. Today we are going to discuss about magnetostatic boundary condition. So in electrostatics, you had already learned about the boundary condition, where we have seen that across a two-dimensional boundary, the parallel component of electric field is continuous, whereas the perpendicular component of electric field is discontinuous. Here you are going to see the converse scenario. So in magnetostatics, you will see that the perpendicular component of the magnetic field is continuous, whereas the parallel component is discontinuous. Okay. So let's get into the details now. So imagine that I have a two-dimensional boundary which is characterized by a surface current K. I have magnetic field above and below this interface. The question is whether the magnetic field is going to be continuous across this boundary or discontinuous. We will consider two components of the magnetic field. One is the perpendicular component and one is the parallel component. First, let's discuss about the perpendicular component. So the perpendicular component above the interface I call B perpendicular above. Similarly, the perpendicular component below the interface I call B perpendicular below. I'm going to assume a Gaussian pillbox, a rectangular pillbox which is intersecting the boundary. So the top side of the pillbox is extended slightly above the boundary and the bottom surface is extended slightly below the interface. Okay. We know that divergence of B equal to 0. So I am going to take volume integral of this equation. So volume integral of divergence of B d tau equal to integral of 0 is 0. I can convert this volume into surface integral using Gauss law. So this is closed surface integral B dot dA equal to 0. Now I need to calculate closed surface integral for this rectangular pillbox. The pillbox has 6 sides, top side, bottom side and 4 sides, right? So I need to calculate this integral for all the 6 sides here. So first start with the top side. So on the top side, the magnetic field is B perpendicular above dot dA. Similarly, on the downside, I have B perpendicular below dot dA. Now, on the top side, as you know, area vector has a direction which is perpendicular to the surface. So, on the top side, the magnetic field and area vector are along the same direction, whereas for the bottom side, magnetic field is along the upward direction, whereas the area vector is along the downward direction. Since these two are along the opposite direction, I put a minus sign here. Okay. So that covers top and bottom side. What about the other 4 sides? In the case of these 4 sides, you will notice that the magnetic field and the area vector are perpendicular to each other. The magnetic field is in the vertical direction, whereas area vector is going to be along the horizontal direction. Since the dot product of two perpendicular vectors is 0, you don't have to bother about the surface integral for all these 4 sides. Okay. So essentially, closed integral B dot dA is nothing but integral B perpendicular above dot dA minus integral B perpendicular below dot dA. Since the magnetic field and area vector in these two terms are along the same direction, the dot product can be replaced by a normal product. Also, we are talking about uniform magnetic fields here, which means I can take the magnetic field outside the integral. So closed surface integral B dot dA is nothing but B perpendicular above integral dA minus B perpendicular below integral dA, which is equal to 0. You can take one of these terms to the right hand side. Integral over dA is common. You can cancel that. Then you get B perpendicular above equal to B perpendicular below. In other words, the perpendicular component of the magnetic field is continuous across any boundary. Coming to the parallel component, so this is the direction of the parallel component. I have B parallel above the boundary, similarly B parallel below the boundary. Now for the analysis, I am going to consider a rectangular Amperian loop intersecting the boundary, just like the pillbox case in the previous example. The top side of the Amperian loop is extended slightly above the boundary and the bottom side is extended slightly below the boundary. Let L be the length of the one of the sides of this Amperian loop. I'm going to apply Ampere's law here. Closed integral B dot dl equal to mu naught I enclosed, where I enclosed is the current enclosed by this rectangular Amperian loop. Once again, in order to calculate the closed integral B dot dl, I need to calculate integral over all the four sides. So in the top side, I have B parallel above dot dl. Similarly, at the bottom side, I have B parallel below dot dl. In the top side, the magnetic field and the line element both are along the same direction, whereas at the bottom side, you can make out B parallel below is towards the right, whereas the line element is towards the left. Since we have two opposingly directed vectors, I am going to put a minus sign here. Coming to these two sides, you can notice that the magnetic field and the line element both are perpendicular to each other, so the dot product becomes 0 there. So closed integral B dot dl is nothing but integral B parallel above dot dl minus integral B parallel below dot dl. In these two terms, these two vectors are along the same direction, which means I can replace dot product with a normal product. Once again, the magnetic fields being uniform, I can take them outside the integral. So this is B parallel above dot dl minus B parallel below integral dl. So integral dl is the common term. So I can write this as B parallel above minus B parallel below integral dl. Now integral along this side will give you the total length L. So closed integral B dot dl equal to B parallel above minus B parallel below multiplied by length L. Coming to the right hand side, mu naught I enclosed. What is the current enclosed by this Amperian loop? We know that surface current K is nothing but line current I divided by perpendicular length L. So K is I by L, or I can write I equal to K into L. So mu naught I enclosed is nothing but mu naught K L. So L, these are common on either side. You can cancel them, then you get B parallel above minus B parallel below equal to mu naught K. In other words, the parallel component of the magnetic field is discontinuous by an amount mu naught K. So you can combine these two results and write B above minus B below. Remember, in the previous two expression we were talking about the scalar component. Now I combine these two and write it as a vector equation here. So B vector above minus B vector below equal to mu naught into K cross N, where n cap is a unit vector perpendicular to the boundary surface. Having defined the boundary condition in terms of the magnetic field, let's move on to define the same boundary condition in terms of the magnetic vector potential. So in electrostatics, you have seen that the electrostatic potential, which is a scalar potential, is continuous across the boundary. here also you are going to see that the magnetic vector potential is going to be continuous across any boundary surface. So A above equal to A below. Let's see how does this happen. We know that divergence of A equal to 0, right? So if you compare our previous derivation, in the case of perpendicular component, we started with divergence of B equal to 0. And eventually we have shown that the perpendicular component of magnetic field is continuous. So this is the same starting point here. I have divergence of A equal to 0. So if you follow the same procedure as before, you will eventually end up with A perpendicular above equal to A perpendicular below. So the perpendicular component of the vector potential is continuous. Moving on to the parallel component, we know that curl of A equal to the magnetic field B. So take the surface integral on either side. So surface integral curl of A dot dA equal to B dot dA. The surface integral on the left hand side I can convert into line integral using Stokes Theorem. So closed integral A dot dl equal to integral B dot dA. Now integral B dot dA is nothing but the flux through the surface. So flux phi. Now in the case of Ampere's law, we have seen that we have the choice of selecting an Amperian loop of any shape. So I am going to assume a rectangular Amperian loop with negligible thickness. Okay, so the side width is almost 0. Since the thickness is negligible, the magnetic flux through this Amperian loop is almost 0. So I can assume that for all practical purposes, the flux through the Amperian loop phi is almost equal to 0, which means I can now equate closed integral A dot dl equal to 0. Now what is the implication of this? Once again, let's go back to our previous derivation. So here we have closed integral B dot dl equal to mu naught KL. In other words, when closed integral B dot dl equal to non-zero, you get a discontinuity here. You can easily make out that if closed integral B dot dl was 0, then here you will have a 0 term on the right hand side and you will end up with B parallel above being equal to B parallel below. Okay. So follow the same procedure here. We have closed integral A dot dl equal to 0, then you will get an equation A parallel above minus A parallel below equal to 0, or A parallel above equal to A parallel below. So we have seen that the perpendicular component is continuous. Similarly, the parallel component is also continuous. In other words, the magnetic vector potential is continuous across any boundary surface. Quite interestingly, even though the magnetic potential is continuous, if you take the derivative of the potential, that is going to be discontinuous, just like the magnetic field. So once again, let's consider a boundary surface with a surface current K. Now we already we have shown that the magnetic potential is continuous, so I can say A above equal to A below at every point on the surface. Let's assume that our surface lies on the xy plane. So from this expression I can extrapolate that the derivative of the magnetic potential with respect to x and y are going to be continuous, just like the original magnetic potential. So dou A by dou x and dou A by dou y are same above and below the interface. On the other hand, the derivative along the normal direction, which is dou A by dou z, is going to be discontinuous. Okay. So what is the implication of this? We know that magnetic field B equal to curl of A. So I'm going to expand curl of A in terms of the determinant. So I have dou Az by dou y minus dou Ay by dou z x cap plus dou Ax by dou z minus dou Az by dou x y cap plus dou Ay by dou x minus dou Ax by dou y z cap. Okay. Now, what is B above minus B below? We have shown that B above minus B below equal to mu naught K cross N. So let's first calculate the left hand side, B above minus B below. Okay. So this is the expression for B. So you can substitute for B above. For example, the first term then becomes dou Az above by dou y minus dou Ay above by dou z. Similarly, B below will be the first term becomes dou Az below by dou y minus dou Ay below by dou z. Okay. So you can calculate, you can expand B above and B below in terms of the x, y, z components, and we know that dou A by dou x and dou A by dou y both are same above and below the interface, which means when you take the difference of these two, all the derivatives with respect to y and x, these are going to vanish, and you are left with only those terms where the derivative is calculated with respect to z. So B above minus B below equal to minus dou Ay above by dou z x cap plus dou Ay by dou z dou Ay below by dou z x cap. Similarly, coming to the y component, you have dou Ax above by dou z y cap minus dou Ax below by dou z y cap. Now coming to the right hand side of the equation, mu naught K cross N. So from this geometry, we can see that the K vector is along the x direction. Then let's assume that the unit normal vector is along the z direction. So this is x, this is z. Consequently, this is the plus y direction. So how do you identify the direction? Just check whether x cross y is along the z direction. So place your right hand along the x direction, curl it towards the y, then your thumb should be pointing in the z direction. Okay. Now let's calculate what is the direction of K cross N. So K is along the x direction. I am going to place my right hand along the x direction, cross N, N is along the z direction. So I am going to curl my fingers towards the z direction. Then you will notice that your thumb is pointing in the minus y direction. Right? So B above minus B below equal to mu naught K minus y cap. So I have two expressions for B above minus B below. So I am going to equate these two. Then I get minus dou Ay above by dou z plus dou Ay below by dou z x cap plus dou Ax above by dou z minus dou Ax below by dou z y cap equal to mu naught K minus y cap. So what do we do? Let's compare component wise. Let's first compare the x components, then the y components. So on the left hand side, the x components are minus dou Ay above by dou z plus dou Ay below by dou z equal to, on the right hand side I have no x component, so right hand side is 0. So from this I can conclude dou Ay above minus by dou z equal to dou Ay below by dou z. So this is continuous. Coming to the y components, so when you compare the y components, you get dou Ax above by dou z minus dou Ax below by dou z equal to minus mu naught K. In other words, the normal derivative of A parallel to K, because K is along the x direction. So normal derivative of A parallel to K suffers a discontinuity minus mu naught K. So let's combine these two results. So z is the normal direction. So for any normal vector n, I can conclude that dou A above by dou n minus dou A below by dou n equal to minus mu naught k. The normal derivative of the magnetic vector potential is discontinuous across any boundary surface. Before winding up, let's do a quick problem. Check the magnetostatic boundary conditions for a solenoid having n number of turns per unit length carrying a uniform current I. So we have analyzed the case of solenoid before. So for a solenoid having n number of turns per unit length carrying a current I, we know that the field outside the solenoid is 0, whereas the field inside the solenoid is mu naught Ni, and the direction is along the axis, along the z direction. So if you have a large number of turns which are closely wound to each other, then it's almost like you have a continuous distribution of closed loop. In other words, you can imagine that you have an aluminum foil, a two-dimensional foil which is rolled into a cylinder. So both these two are similar geometries. So either you can make your analysis in terms of line current flowing through each of this closed loop, or you can imagine that an equivalent surface current K is flowing along this aluminum foil or the two-dimensional conducting foil, where the magnitude of the surface current is given by n times I. So n is number of turns per unit length. So this is number of turns into current per length. So this is the total surface current. Okay. Let's now apply our magnetostatic boundary condition. So we need to calculate B above minus B below. Now this is the surface at which we are doing our analysis. So B above is nothing but the region outside the solenoid. We know that outside solenoid the magnetic field is 0. So B above equal to 0. What is B below? This is the electric field within the solenoid, which is mu naught Niz cap. Since n into I is nothing but surface current K, I can write B below equal to mu naught K Z cap. So B above minus B below is minus mu naught K Z cap. As you have already noticed, we have an inherent cylindrical symmetry here, which means we can resort to cylindrical polar coordinates for easy calculation. In cylindrical polar coordinates, we have three axes. One is the z-axis, which is in the upward direction. Then perpendicular distance from the z-axis, this is the s-axis. Then I have azimuth angle phi. Now, what is the direction of the n vector? N vector is nothing but a perpendicular vector from the boundary surface. So if this is my boundary surface, then the perpendicular vector will go towards the right, which is nothing but the direction of the s-axis. So n cap is nothing but s cap. Now, what is k cross n? So you can notice here in this diagram, n vector is towards the right and z vector is in the upward direction. And here you can notice the surface current K is going into this plane, which is denoted by this cross. So now how do you calculate K cross n? So you place your right hand in the direction of K, curl your fingers towards n, then you notice that your thumb is pointing in the minus z direction. So K cross n is nothing but minus K z cap. So B above minus B below is nothing but mu naught into K cross n, which is minus mu naught Kz. So we have shown that the magnetostatic boundary conditions are valid for the case of a solenoid. So thus we come to the end of chapter 5, magnetostatic, and in the next session you will learn about magnetostatics in the case of material media, and that will be handled by Madhu ma'am. Thank you.